Hello and welcome to this demonstration of the MDEO-Cloud tool, an extensible platform for model-driven optimization. Projects serve as the central organizational unit of the platform. Let me now demonstrate this platform using the class responsibility assignment problem, which I'm going to open here. On the left side, you can see the file tree, which contains all the files defining the optimization problem. Thereby, the core artifact is the meta model, which I'm opening here. It defines the problem and the solution space, and can be edited using our custom blended graphical textual editor. Both views are live synced and fully support editing the meta model, which I demonstrate by completing the CRA1. First, I create the attribute class graphically, followed by creating the extends edge. Next, I define the data dependency association textually. Additional supported features include refactoring as well as automatic layouting. Next, models are used to define the concrete problem instance to solve. Here I provided 5 different models. As you can see, it uses a highly similar blended graphical textual editor, with the goal to improve usability by using rather similar syntaxes for all our diagrams, which was one of the primary motivations to introduce these new languages. MDEO-Optimizer uses an evolutionary algorithm, where new solution candidates are created based on existing solution candidates, meaning models. To define such search operators, we use our endogenous model transformation language, for which I open the assigned feature model transformation here. Heavily inspired by existing graph-based model transformation languages, it consists of an outer UML activity diagram-inspired control flow graph with embedded graph transformation match patterns. The example model transformation shown here consists of a singular match pattern. Its graphical syntax is highly aligned with Eclipse Engine. Elements to create are highlighted in green and marked with create. Further, we support both positive and negative application conditions, where negative application conditions are marked with forbid and represent patterns which must not be found in the graph in order for the pattern to match. To guide the evolutionary search, constraints and objectives implemented as model queries are required. We utilize the crypt language, a statically typed model query and constraint language heavily inspired by Kotlin and the Epsilon object language. In this project, all guidance functions are defined in this scripts file I just opened. Each constraint and objective is implemented as a function returning a number. For example, on the top, you can see the minimize classes features function, which returns the number of features not yet assigned to a class. As I have now introduced all important parts of the optimization problem, let me continue with the config language, which fully defines an optimization problem by referencing the previously introduced artifacts. It is defined as an extensible configuration language, where plugins contribute individual sections. For example, the first 2 sections are contributed by the general model-driven optimization plugin. First, the problem section defines the meta model and model, followed by the goals section, which defines objectives and constraints by referencing script functions. The following sections are contributed by the MDEO-specific plugin. The search section defines mutation operators. In this example, you can see 4 referenced manually defined model transformations. Additionally, like the existing MDEO, automatically generating consistency-preserving mutation operators is supported. Following, the solver section chooses and configures the evolutionary algorithm. Last, a new runtime section allows to configure aspects such as timeouts and maximal resources used. By clicking on the Run button in the top right corner, the optimization running in the cloud-based backend is started. When I hover over its entry, I'm continually informed of its progress, in particular the number of executed model transformations. Further, notifications in the bottom right corner inform the user when an execution completes, which is helpful for realistic longer-running optimizations. By double-clicking a completed execution, I can open its Markdown report. For optimization runs, this report contains Pareto optimal models, including their objective and constraints values. For this CRA run, a single solution was generated, which you can also see on the left in the file tree associated with this optimization run. Further, we generate several graphs, providing additional insights into the optimization process. In particular, we show how many transformations are executed in each generation, how the hypervolume quality indicator changes over time, as well as the iteration time of each generation. In summary, MDEO-Cloud offers you a web-based, efficient and easy-to-use possibility to model and execute evolutionary search-based optimization problems. Thank you for your attention.